This video is brought to you by mywayteaching.com.
So in this part, we'll study about principle of moments. Okay. See, an ideal lever is essentially a light. It is a light rod which is pivoted at a point along its length. The point is called as a fulcrum. You can see that. An ideal lever is just a light rod with a point pivoted at a point along its length, and that pivoted point is called as fulcrum. Okay, a seesaw on a children playground is a typical example of a lever. Two forces F1 and F2 parallel to each other and usually perpendicular to the lever, as you can see in this figure. Two forces F1 and due to F2, which are parallel forces but perpendicular to this lever, act on the lever at distances d1 and d2 respectively from the fulcrum. This is the fulcrum. Okay, it acts at a distance of d1 and d2 from this fulcrum. The lever is a system in mechanical equilibrium. Let R be the reaction of the support at the fulcrum. This R is the reaction force that acts at this point. Okay, R is directed opposite to the forces of F1 and F2. For translational equilibrium, the total force acting on the system must be equal to 0. So R minus F1 F2 must be equal to 0 for translational equilibrium. For considering rotational equilibrium, we take the moments about this fulcrum. So the sum of the moments must be 0 for considering the rotational equilibrium. That is d1 f1 minus d2 f2 must be equal to 0. Isn't it? This is rotational equilibrium. So normally the anti-clockwise or clockwise moments are taken to be positive. Anti-clockwise moments are taken to be positive, or we can say vice versa also, not a problem. So R acts at the fulcrum itself and it has zero moment about the fulcrum. This R, it acts at this fulcrum point and it has a zero moment. There is no distance, so it is 0. So in case of a lever force F1, it is usually some weight to be lifted, isn't it? At these two endpoints will be having some weights. It is called as load, and its distance from the fulcrum d1 is called as load arm. So this weight at this force at the point A is called as load, and this distance d1 is called as load arm. Okay. And the force F2 is the effort applied to lift the load, and D2 is the effort, it is the D2 of the effort from the fulcrum is effort arm. This is effort F2 and this one is effort arm. This because this is the effort to lift F1, isn't it? You just remember that seesaw game, you'll get that. So we can write this equation 2 as d1 f1 is equal to d2 f2, isn't it? So load arm into load is equal to effort arm into effort. So the above equation expresses the principle of moments for a lever. So incidentally, the ratio of f1 by f2 is called as mechanical advantage. The ratio of these forces is called as mechanical advantage. F1 by F2, that is equal to D2 by D1. If the effort arm D2 is larger than the load arm, the mechanical advantage is greater than 1. Mechanical advantage greater than 1 means a small effort can be used to lift a large load. Okay, there are several examples of a lever around you besides seesaw. The beam of a balance, it's a lever. Okay, that is one simple example. You can find several other examples also. Okay, so now let us study what is center of gravity. See, many of you you have the experience of balancing your notebook on tip of your finger, isn't it? And you can see in this figure balancing a cardboard on tip of a pencil. The point of support is G, that pencil tip. That is called as center of gravity. Okay, you can see that here G. Take an irregular shaped cardboard and a narrow tipped object like pencil. You can locate by trial and error a point G. Means at what point you can balance with that pen tip or pencil tip on the cardboard, where it can be balanced on the tip of the pencil. This point of balance is nothing but center of gravity of the cardboard. The tip of the pencil provides vertically upward force due to which the cardboard is in mechanical equilibrium. As shown in this figure, the reaction of the tip is equal and opposite to that mg. So this R is equal to mg. Okay, the reaction force will be equal and opposite to mg, that is total weight of the cardboard, and hence the cardboard is in translational equilibrium. It is also in rotational equilibrium. If it were not so, due to the unbalanced torque, it would tilt and fall. So if the whole system is not in translational and rotational equilibrium, then it will fall, because the total torque must be zero and even the force must be zero acting on that particular cardboard. The center of gravity of the cardboard is so located that the total torque on it due to the forces M1G, M2G, means the system of particles. Here all these are system of particles. The total force due to all these system of particles must be 0. If R1 is the position vector of the ith particle of an extended body with respect to its center of gravity, then the torque about this center of gravity due to the force of gravity on the particle is given by the torque on the center of gravity due to the force of gravity. That is given by same the position vector Ri mi. Here we have to consider acceleration due to gravity, and the total gravitational torque about the center of gravity must be 0. The total gravitational torque must be 0. Okay, so we can define the center of gravity of a body as that point where the total gravitational torque on the body is 0. Okay, we notice that from the equation that we studied, G G is same for all the particles. Okay, from this above equation, that is torque G is equal to torque Ri into Mi into G. This G is constant. See here, it will not change with the system of particles. So it is constant for all the particles, and hence it comes out of the summation. So this gives, since G is non-zero, Mi Ri is equal to 0. Agreed? Since G is non-zero, we know that it has some particular constant value. Mi Ri is equal to 0. It's true. So the position vectors are taken with respect to CG. Now, in accordance with the reasoning, okay, which in accordance with the reasoning given in the equations that we studied, okay, in with respect to this equation, x is equal to sigma mi xi by m. If the sum is 0, the origin must be the center of mass of the gravity, isn't it? So, thus the center of gravity of the body coincides with the center of mass in uniform gravity or in gravity free space. Okay. This is true because the body being small, g does not change. D does not vary from one point of the body to the other. So that is true. The center of mass, it coincides with the geometric center of the body. So now let us study the another way of determining the CG of an regular shaped body like a cardboard that we saw now. Now how to determine this center of gravity in case of irregular bodies? See, if you suspend the body from the point like A, the vertical line through A passes through the center of gravity. You can see that this point A and it passes through the center of gravity. We then suspend the body through other points like B and C. The intersection of verticals gives the center of gravity. The intersection of all these verticals gives this center of gravity. Okay, this is about the finding out the center of gravity in case of irregular bodies. Now let us solve simple problem. The question is a metal bar 70 centimeter long and 4 kg in mass supported on two knife edges placed 10 centimeter from each other. A 6 kg weight is suspended at 30 centimeter from one end. Find the reactions at the knife edges. Assume the bar to be of uniform cross section and even homogeneous. Okay. So now try to understand the question, then we can find what they're asking. They're asking us to find out the reactions, that is R1 and R2, isn't it? Yes. So this figure shows the rod AB. So the positions of the knife edges, that is given by K1 and K2. The center of gravity of the rod is G. The weight is acting here and the suspended load at point P. Note the weight of the rod W acts at its center of gravity, isn't it? Here they have shown that the weight of the rod, it acts at its center of gravity. The rod is uniform in cross section and even homogeneous. Hence, G is at the center of the rod, which means it lies with the center of the mass. The center of gravity is equal to center of the mass. So here they have given AB is equal to how much? 70 centimeter. AG is equal to, since it lies with the center of mass, it is given with 35 centimeter, half of this AB. And AP is equal to 30 centimeter. And PG is equal to 5 centimeter. Because that is AG minus AP, isn't it? And AK1 is equal to BK2. That is given by 10 centimeter. And K1G is equal to K2G. That is given by 25 centimeter. Okay, here it is AK1, BK2. It is 10 centimeter. and K1G, K2G is 25 centimeter, and I have given the weight of the rod is 4 kg and the suspended load that is given by 6 kg. Okay. R1 and R2 are the normal reactions of the support at the knife edges. We should find out this R1 and R2. For translational equilibrium of the load, what is the things to be considered? Yes, for translational equilibrium, R1 plus R2 minus W1, the total forces must be 0. See, W1 and W act vertically down and R1 and R2 act vertically up. So the direction change. For considering rotational equilibrium, we take moments of the force, isn't it? A convenient point to take the moments is about the center of gravity. So the moments of R2 and W1 are clockwise. R2 and W1, the moments are clockwise and that is positive, whereas the moments of R1 and W are negative. For rotational equilibrium, we should consider the moments that is minus of R1 into K1G plus W1 into the arm that is PG plus R2 K2 into G that is equal to 0. It is given that W is equal to 4 and W1 is equal to 6. It is given, right? 4 kg and 6 kg, and G is acceleration due to gravity, and we can take it as how much? 9.8 meter per second square. So after substituting the numerical values, we get from the first equation R1 plus R2. We know W1 is 6 and W1 is 6 and W is 4. So R1 plus R2 will get it as 10 kg. Okay. If you convert in terms of Newton, we will get it as 98 Newton, since the unit of force is Newton. And similarly, if you substitute in the rotational equilibrium equation, we'll get the equations as minus, we know that is 25 centimeter K1 into G. So if you convert it into meter, it becomes 0.25. Similarly, 0.05 W1 plus 0.25 R2, that is equal to 0. We know the value of W1. So if you simplify this further, we get R1 minus R2 is equal to 1.2 G, that is 11.76 Newton. Okay. So from the equations 1 and 2, the first equation, what we get, R1 plus R2 is equal to 98 Newton, and the second one is R1 minus R2 is equal to 11.76 Newton. If you simplify this, we get the value of R1 54.88 Newton, and the value of R2 after substituting in any one of the equation, we get 43.12 Newton.